Hello everyone, welcome to the course on Fundamental of Electronics Engineering. This is lecture 1 and in this lecture we will see the MOSFET. So first, the MOSFET, it stands for metal oxide semiconductor field effect transistors. They are also known as IGFET, which is known as insulated gate field effect transistor. Here the gate terminal is insulated with the help of some oxide layer. Now the MOSFET is also a voltage control device. Likewise, we have seen in case of BJT that BJT is a current control device, whereas MOSFET is a voltage control device. Now we'll talk about the construction part. So the MOSFET, basically it is a 4-terminal device. So the first terminal is source, drain, gate and body. This body is also known as substrate, means all the terminals like drain, source and gate, they are designed over the substrate. So these MOSFET find various applications in the analog circuits and digital circuits. So the MOSFET, the advantages of MOSFET over the FETs, which is field effect transistors. So they are mainly designed to overcome the drawbacks like high drain resistance. In case of FET, there is a high drain resistance and the input impedance is also moderate. So we can say that FET was not very suitable for amplification purposes. We'll be seeing in this MOSFET that MOSFET will provide a very high input impedance due to the insulation layer present at the gate terminal. So this is the advantage. So that's why the MOSFET are mainly used over the FETs. And also one major drawback for FETs are their slow operation. So if we want an application which required fast speed, so we'll be preferring the MOSFET over the conventional FETs. Now we will see what are the classifications of MOSFET. MOSFET are classified as depletion type MOSFET and enhancement type MOSFET. Now this term depletion and enhancement is corresponding to the channel present in the MOSFET. So we'll see in the construction part that in the depletion type MOSFET, the channel was already present during the construction, whereas in the enhancement type MOSFET, the channel was absent and the channel will be formed during the operation. So this is the major difference between the depletion type and enhancement type MOSFET. So in this lecture, we'll be mainly focusing on the depletion type MOSFET. First we will see what is the construction part of this MOSFET, how a depletion type MOSFET is constructed. After that we will see the working part of the MOSFET and we will see the characteristics. What is the current versus voltage relationships corresponding to the MOSFET. Now these MOSFETs are, the working of the MOSFET is very similar to that of the conventional JFETs. So here we have the symbolic representation of MOSFET and here we have the low power MOSFET. So 2N3797, this is the number corresponding to this particular device. Now we'll see the construction. So as the name is metal oxide semiconductor, so there is no direct electrical connection between the gate terminal and the channel. We have seen it is a 4-terminal device. So here we have the gate terminal. We have two N-type material which are acting as a drain and source terminal. And we have the substrate which is also termed as body. Substrate and body means the overall terminals are basically embedded on the body and with the help of this is called as SiO2 layer. So this SiO2 layer basically it acts as an insulator between the gate terminal and this is called as channel. So why the name is N-channel depletion type MOSFET? Because the material here we have is of N type. So in N-type depletion type MOSFET, we can say that the channel is of N type and also the drain and source terminal is of N type, whereas the substrate is of P type. Now with the help of some metallic contacts, we can define the terminals: drain, gate, source, and we can say substrate or body. So we can say that due to this SiO2 layer, the input impedance of MOSFET or the input impedance of this particular device is very high. And if we remember that for a good amplification, the input impedance of the amplifier should be very high, whereas the output impedance of the amplifier must be as low as possible. Now due to this particular fact that the gate is insulated, this is also known as IGFET, insulated gate field effect transistor. Now we will see the working part, how a MOSFET is, we can see the operation also. Now from this particular picture we can say that there are two voltages. One voltage is we are applying across drain and source terminal, and another voltage we are going to apply between gate and source terminal. So how can we see the operation? So we'll be seeing the operation in two steps. First of all, we'll be having gate to source voltage VGS equal to 0. Means we are not applying any voltage across the gate and source terminal. We'll be applying some voltage across drain and source terminal, which is termed as VDS. One more important point is that body and source are internally connected. We can observe here that body and source are internally connected to minimize the body effect. Now we will see that what will happen if gate to source voltage is 0 and we are going to increase the value of VDS. So as we can say that as VDS increases means drain terminal will become more positive with respect to source. So what will happen? This drain terminal will attract more number of electrons from the channel. So as a result, what we can say that as VDS increases, more number of electrons are attractive towards the drain side. We can say that as a result ID increases. This is the direction of current ID. And since the gate terminal is insulated, so we can say that the gate current IG is equal to 0. IG equal to 0. If we are further increasing the value of drain to source voltage, so we can say that ID further increases like this, because it will attract more number of electron in the upward direction. So we can see that gate to source voltage is 0 by the direct connection from one terminal to other, means we are making short gate to source terminal, and VDD is applied, or we can say that we are applying drain to source voltage. As a result, we have seen that more number of electrons are attracted towards the drain side from the channel. So this result in a similar kind of current that flows in the channel of JFET, means the operation is quite similar to that of JFET. So the resulting current with VGS equal to 0 continues to be labeled as IDSS, means it will be gaining a saturated value which will be known as IDSS, drain to source saturation current. Drain to source saturation current. So in the next part we will see, now we'll be making gate to source voltage negative and we'll be having VDS, we'll be fixing VDS at some positive value. So what will happen? Please see that when this gate terminal is more negative, So what happen is that more number of holes are attracted towards the channel, because this substrate is of p type and the majority charge carriers in p type are holes. So as the majority charge carriers are hole, that means more number of holes are attracted towards the gate terminal, and we can say that due to this recombination there is a formation of depletion region. There is a formation of depletion region, and as a result the width of this channel W, we can say it reduces. So we can write down here that as VGS will become more negative, as VGS increases in the negative direction, then it will result in decrease in the width of channel. If the width of the channel decreases, so we can say the current ID, which was flowing from drain to source terminal, it reduces. It reduces. So the principle here is that the name is depletion type MOSFET, means as we are applying the gate to source voltage, when gate to source voltage is negative, then we can observe that the width of the channel reduces. The channel get depleted. So this is a principle behind the depletion type MOSFET. Now here, as VGS is set to some negative voltage and we have fixed the value of VDS, as all the holes are majority in the P side, they get attracted towards the channel, and due to this recombination between the holes and electrons will occur, and that will reduce the number of free electrons inside the channel, that channel which is available for the conduction. So the more negative bias, we can say that the higher the rate of recombination, as the rate of recombination increases, we can say that the drain current ID, it reduces. Now when VGS is greater than 0, means when gate to source voltage is positive, please see that when it will become positive, then it will basically attract the minority electrons available inside the substrate or inside the body. So as a result, we can say that, let's say previously we have 100 electrons, so due to this positive voltage, the electrons get attracted towards the channel, and it will increase the number of free charge carriers, and as the number of free charge carriers increases, it strengthens the channel, means the width of the channel increases. So as VGS is positive and we are increasing the value of VGS, it will increase the width of the channel. Now as the width of the channel increases, it will result in the drain current to increase. So that means this type of operation is referred as enhancement. This type of operation is known as enhancement because current increases, ID increases. Whereas in the previous situation, what we observed that as we are providing VGS more negative, then the current ID decreases. So that is called as depletion. So we can say that this depletion type MOSFET can work under both the conditions, means in the depletion type MOSFET as well as in the enhancement type MOSFET. So it is also named as DE MOSFET because this D and E, they are the mode of operation. So we can observe clearly in the characteristics that what is D mode, what is E mode. So first of all, we'll be seeing the characteristics. Now what are the characteristics? We can clearly see from this particular circuit that we have output characteristics which is between ID and VDS for different values of VGS, which is termed as drain characteristics or output characteristics. Similarly, we have the characteristic which is between ID and VDS for different values of VDS. So this term is referred as transfer characteristics because we have taken one variable from second port and one variable from first port. So this is known as transfer characteristics. So we can observe the transfer characteristics first. So I'm having an equation also which correlates drain current with gate to source voltage, and the equation is ID equal to IDSS 1 minus VGS by VP whole square. So we can clearly see that when VGS is equal to VP, what will happen? When VGS is equal to VP, what will happen? The current ID will equal to 0 because we are aware that the channel basically disappear and the current will be equal to 0. So this is, we are talking about N channel. That means for N channel the pinch off voltage is what? It is negative. So we can clearly observe that in this particular region the MOSFET, the N channel depletion type MOSFET is working under the depletion mode. Whereas if we are increasing the value, means if we are making VGS positive, so that means we are strengthening the channel. So if the channel is strengthening, that means ID increases. So here we can say that if VGS is positive, so we can say ID increases. So this particular region, if we can observe, then it is known as enhancement mode of operation. So this is called as transfer characteristics. Now the characteristics between ID and VDS, this is called as drain characteristics or output characteristics. So ID versus VDS for different values of VGS. So what we initially observe, that when VGS equal to 0, initially current increases, and finally what will happen? It will gain a saturated value which is termed as IDSS, drain to source saturation current, like this. Next, what is the curve when VGS is negative? We are already aware that when VGS is negative, that means ID decreases. So naturally the curve will shift in the downward direction. This is for VGS equal to -1. Now further, as we are increasing VGS in a negative direction, that means the width of the channel reduces and it will result in the drain current to reduce. So that's why we can observe that the curve is shifted in the downward direction. Whereas if we are applying VGS positive, then we are basically strengthening the channel, and due to which the current ID increases. So the curve will shift in the upward direction. So we can say that in this particular drain characteristics, we can mark both the modes. This is called as enhancement mode of operation and this is known as depletion mode of operation. It is called as depletion mode of operation because current reduces. So we can mark the region also, this where the current is linear, this is called as linear region. Here we can say this is known as a saturation region, where the current get saturated. This is called as a ohmic region, ohmic or linear region. And below this, where the current is 0, this is called as cutoff, because in this particular region we can observe that the current is 0. So we have basically marked all the regions: saturation region, cutoff region and ohmic region or linear region. So these are the characteristics of N-channel depletion type MOSFET. Now before starting with the P-channel depletion type MOSFET, what we can say that in N-channel, what we can observe here, that for N-channel, if VGS was negative, then current basically decreases, ID decreases, and when VGS is positive, that means current increases. So what will happen for P channel depletion type MOSFET? So we'll see that first the construction part, that in the P channel MOSFET, what we are having, the drain and source both are of P type. Now the substrate or body, this is of N type. And we are also aware, while seeing the operation, the body and the source, they are internally connected to minimize the body effect. And also we have the SiO2 layer which act as a dielectric between the gate and substrate, or gate and channel basically. So to see the operation of this particular device, what type of voltage we can apply? So first of all, we can apply VGS positive when VGS is positive, and we can note down here that when VGS is negative. So when VGS is positive, that means what will happen? More number of electrons are attracted towards the channel. And due to the attraction of channel, there is a recombination happens in the channel area, and due to which the number of free charge carriers, which are holes, they will become very less, and due to which the width of the channel reduces. And as the width of channel reduces, the drain current ID reduces. So basically it explains the depletion mode. Whereas when VGS is negative, then what will happen? It will attract the minority holes, minority charge carriers holes, which are present inside the body or substrate. So due to which the concentration of holes in the channel increases, and as the concentration increases in the channel, we can say that it strengthens the current, ID increases. So W increases and ID also increases. So this mode of operation is known as D mode, and this mode is known as E mode. So the MOSFET, the depletion type MOSFET, can work under both the modes, D mode and E mode. So now we will be seeing the characteristics. First we will see the transfer characteristics, and afterwards we will see the drain characteristics. So if we can observe the characteristics for P channel depletion type MOSFET, it is quite similar, but it is just a mirror image of the N channel. Means for P channel MOSFET, now the pinch off voltage means the voltage at which the channel width will become 0, means there will be no conduction between the drain and source terminal. So what happens when there is no conduction? As a result, the current will become 0. And when VGS is equal to 0, we can have the equation also that ID equals to IDSS 1 minus VGS by VP. We can observe mathematically also that when VGS equal to 0, the current ID is equal to IDSS. So we have this particular point, and when VGS is negative, then the current naturally increases. So this mode here is known as D mode of operation, or this is D mode, depletion mode, whereas this is known as E mode, this particular area. So this is the transfer characteristics of a P channel depletion type MOSFET. Now we will see the drain characteristics. So how a drain characteristics will look like? So first of all, the drain characteristics is between ID and VDS. Now we need to remember that for N channel VDS was positive. So for P channel VDS must be negative. This is a negative quantity, means we are increasing the value VDS but in a negative direction. So first of all, we observe the characteristics for VGS equal to 0. What will happen? Initially we have the linear curve, which explain the ohmic region, where the current increases linearly. And when VGS is positive, we have observed in our last slides that when VGS is positive, the current ID decreases. So the curve will shift in the downward direction for various values of VGS. The curve will shift in the downward direction. And similarly, when VGS is negative, so we can say that ID increases and the curve will shift in the upward direction. So it explains this mode. This is known as enhancement operation. Enhancement mode of operation, and this particular is depletion mode of operation. So after this, we can mark the region of operation also. So first is ohmic, or we can say linear region, because we can observe that in this particular region the current increases linearly. What will happen in this particular region? Here the current will become saturated, so it is termed as saturation region. And when the drain current ID is 0, the region which I am marking here, this is known as cutoff region. Cutoff region. Also we can observe that for a P channel depletion type MOSFET, VP, pinch of voltage, will become positive, whereas for N channel the pinch of voltage was negative. So next is the symbol. Symbol is quite important. We can see first we have the N channel. So if we remember that for an N channel depletion type MOSFET, the substrate or the body is of P type, and for P channel the substrate or the body is of N type. So accordingly the direction of current will be inward, whereas here the direction of current is outward. So these two pictures are quite clear. Now if we can observe this upper figure and this lower figure, so we can observe that the substrate or the body, they are internally connected. We have also assumed during the operation part. So we can interconnect the substrate and body and source are internally connected. So we have the another kind of symbol. So this is for N channel depletion type, and these two are for P channel depletion type. First we have all four terminals: drain, source, gate and body. And if both are connected, body and source are internally shorted, then we can say that we have only three terminals left for the operation. One is drain, source and gate. So these are the two terminals which we generally use. So now the application part of MOSFET. So the MOSFET, basically due to this high switching speed, the MOSFET are used as an amplifier, and they are extensively used in the RF applications, radio frequency application. It also acts as a resistor, which is called as voltage variable resistor, VVR, because in the starting slides we have seen that MOSFET or FET work as a voltage control device, whereas BJT is a current control device. So we can observe, we have already observed that in the active region of operation, the resistance of the device varies. We have observed in the characteristics that initially the current increases linearly, afterwards we have the saturated current. That means in this particular region we can observe that the resistance of the device varies. So the MOSFET is a voltage variable resistance. So it can behave as a passive element like a resistor, capacitors and inductors. DC motors can also be regulated by the help of power MOSFETs. And due to the high switching speed of MOSFET, it is an ideal choice for design of a chopper circuit. Chopper circuit are basically DC to DC conversion. DC to DC, the circuits are chopper circuits. And there are other further applications of MOSFET. We can have the CMOS circuits also, complementary metal oxide semiconductor field effect transistors. So in the next lecture, we will be seeing the enhancement type MOSFET. So these are the references. Thank you.